All right, so we're going to review the needs for Lab3 for the firmware component, at least for the first deliverable. So what I've done is I put together a pretty lengthy set of slides that goes through all of the basic items and kind of walks you through the basic things that you need. Now, we've discussed a lot of this already in class, and I've presented a lot of these slides, but I've beefed them up a bit to kind of point you in the directions that you need. So you'll see here, so I give this overview here, and there's a lot of different sections here. So basically I run through all of the different sections that are contained within this, okay? And each of these sections provides some guidance for Lab 3 Deliverable 1. All right, now as I've said before, Lab 3 Deliverable 1 is the basic bare bones structure of your firmware. You'll add to it and you'll do some additional things as you go through this, but the core of your firmware will be ready to go once you get through deliverable 1. All right. Okay, so all that said, I've got a couple of things here. So the basic firmware structure. All right, so this is going to talk about the overall needs of the system. Then the basic structure of main.c, so what's included in our main function. And then I talked about this in class. EAllow protected registers. So essentially, EAllow and EDIS, what are they? And how to figure out which registers are EAllow protected. The basic concept of interrupts, again, I've talked about this in class, but this is an important thing to kind of revisit. Interrupt setup, all right? This particular function, or this section, interrupt setup, talks specifically about how we set up the use of interrupts on our microcontroller, the F2A335. All right, so it's very specific to that. Now, it's a general setup, so it's one that we can use essentially for the external interrupt, for the ADC interrupt, and the PWM interrupt. Okay. The GPIO setup, I talked about this in class as well. The section here on GPIO setup also talks about the external interrupt setup. Okay. PWM Init and ADC Init basically talk about how we initialize the PWM and ADC modules. All right, there's a little bit more that we need to include than what we had previously, because essentially now we have to include some things to set up the interrupts. I then talk about ISR basics, so some fundamental things that need to be included in any ISR or any interrupt service routine. And then I talk specifically what needs to be in the interrupt service routine for the external interrupt, for the PWM interrupt, and the ADC interrupt. All right, so all of these things, all of these sections provide guidance specifically for Lab 3 Deliverable 1. Now, in addition to the specific guidance that they're providing, they provide a little bit of a general overview of all of the concepts that are involved and required for us to understand for this lab. So I'm going to talk real quick about some of these things here. So the basic firmware structure, let's kind of remind ourselves as to where we're ultimately going. All right, so essentially this is our system. So the electrical engineers are responsible for everything up here. All right, so we'll have a PV panel, which in the lab is just going to be a power supply that's going to be connected to the inverter board that the electricals have designed. And at the output, I'm going to have a filter. All right, now, in addition, I've got the microcontroller, and the microcontroller is going to generate ultimately 4 PWM signals. In Lab 3, Deliverable 1, you're only generating 2 PWM signals. You don't have a full bridge yet. You're going to use the half bridge that you used in Lab 2. Okay? Ultimately, you're going to have some signal conditioning circuits, so our op-amp circuits, right, that are going to take real values like the voltage on the panel or the current in the panel and convert them to the 0 to 3 volt range that need to go into the microcontroller. So I've got inputs from those signal conditioning circuits. I've got an input on external interrupt 3, and I have outputs on the PWM signals, right? So 2 sets of inputs, the 8 analog inputs, the external interrupt 3, and then 1 set of outputs, the PWM signals. Okay? Now, I've talked about this before, but I want to sort of remind ourselves what external interrupt 3 is. Okay? In a real system, it's important that the voltage coming out of the inverter that we create is aligned in phase with the voltage on the grid, okay? So what that means in this particular case, so imagine that the grid voltage, so here's a grid voltage sinusoid, that would be V grid right here. So V grid is shown by this. Essentially what I want to know is I want to be able to figure out the phase of that waveform, which essentially means that I want to get some sort of a pulse that goes high every time this voltage passes through 0 degrees. So it passes through 0 degrees whenever the voltage goes from negative to positive. So basically at this point right here, all right, and at this point right here, all right, so maybe I'll show that with my marker, right? So at this point here and at this point here, all right, where the zero crossings occur. The way we represent that is using a square wave here, right? So what I see is that every time the voltage here is positive, I have a square wave that is set to 3.3 volts. It's high, okay? And every time the waveform is negative, the value of that square wave is 0. So in other words, what that tells us is every time this square wave goes from 0 to 1, so from 0 volts to 3.3 volts, what we call every rising edge of that waveform, which I mark with these sort of arrows, every rising edge of that waveform is basically the zero crossing of the voltage. I want to know when that occurs to make sure that my PWM is synchronized to the grid voltage. Okay? All right? So those are the basic functions. I need to be able to take in this external signal. I need to be able to take in some analog input signals. And I need to be able to generate the appropriate PWM signals. Okay? Now, again, I've described this before, all right, but in your final PWM or your final piece of code, right, your duty ratios are going to be sinusoidal functions, right? And so you can get the sine function from math.h, right? You can include math.h and you'll get the sine function, which remember is defined in radians. Okay, so the PWM ISR, what it's going to do is the PWM ISR is going to compute the duty ratio using the sine function, and it's going to have to keep track of theta. It's going to have to keep track of the angle. Okay, the theta value is computed. Simplest way to do it is by counting the number of PWM cycles since the last zero crossing. In other words, we know that if we have our switching frequency, our PWM frequency, if that's 30 kilohertz, okay, then I know that the time is 1 over that, all right, which works out to be 33.3 microseconds. So every 33.3 microseconds, I count up, all right? And every 33.3 microseconds, I have another PWM interrupt. So I can use that value in here to calculate theta, all right? And I can come up with a relatively simple and straightforward way to do that, all right? So if I keep track of the number of PWM cycles that have happened since the last zero crossing, this becomes really easy ultimately for me to be able to do. All right. So every time the grid voltage crosses through 0, I'll have that external interrupt. So that external interrupt that I'm showing, down here. All right. This guy, that external interrupt happens every time I pass through 0. Inside that external interrupt, I'm going to set angle theta back to 0. Just hard set it back to 0. The other thing I need to do is inside here, I will compute the average value of IPV and VPV. Now in deliverable 1, all you need to do is just calculate just for a single variable, right? You're not using IPV or VPV. We're not doing any control with it. We're just learning how to use the ADC to compute these averages. All right. So I've talked before about how you would do that, right? So if I know how many samples I have recorded, okay, since the last external interrupt, it's easy for me to just sum all the samples that I've gotten since the last external interrupt and divide by the number of samples. Okay, so remember, one thing I guess I didn't say here, right, but the PWM interrupt triggers the ADC interrupt. So essentially what that means is that I'm also sampling at 30 kilohertz. Now I know that the voltage, the panel voltage and the panel current don't change at 30 kilohertz. So what I'm doing is I'm averaging over each 60 hertz cycle, right? So I take, in that 60 hertz cycle, so 60 hertz is about 16 milliseconds, I'm going to have, I don't know, a couple of hundred samples of VPV and IPV. So I'm going to average over all those samples, okay? So that's the sort of the basic operations that we need. All right, now for deliverable 1, since I only have a half bridge, my duty ratio needs to be a little bit different. So in this case, I'm gonna have an average duty ratio of 0.5, and then I'm gonna sinusoidally allow it to vary with an amplitude of 0.25. Right? So this means that D max will be 0.75 and D min will be 0.25. Okay? All right, so in deliverable 1, step 1, I'm going to need to use EPWM 1A and 1B, all right, which control the fast side, right? So I call it the fast side. Right now, that's all I have is a fast side, right? And then I'm going to need to implement this rising edge interrupt, all right, which I'm going to do simply using the function generator, right? So I keep talking about the grid voltage, but you're going to create a 60 hertz square wave from the function generator. We're not ready to connect up to the grid, and you're going to use external interrupt 3 for that signal. All right. Now for deliverable 1, step 2, basically what you're doing is you're adding in the ADC. All right, and we're really just trying to get ourselves familiar with how to use the ADC. So essentially what I do is I use the code, I guess this should say from deliverable 1, deliverable 1, step 1. So I use all the code that I had before, all right, from the first part of the deliverable, except that I'll add the ADC, okay? Inside the ADC ISR, I'll measure one signal using the signal conditioning circuit. And then inside the external interrupt, I'll compute the average value, okay? Now, ultimately, it's going to be the average value of IPV and VPV. In this particular case, it's just going to be the average of the one signal that you're sampling. Now, the other thing that you're going to need to do is learn how to properly use the ADC, which means you need to go through the calibration step, okay? Which basically says the calibration step is how do I figure out how to take the value that is going to be here inside the ADC. Remember, I've got a 12-bit ADC, so that means I'm going to get a value out of my ADC that's an integer between 0 and 4095, and I have to figure out how does that ADC integer go back to an actual analog signal that I measured in the real world, okay? That calibration step is important. I talked about that in class. I'll do a separate video on that, okay? All right, now to do all of this, essentially what I'm going to need is an ADC init function, a PWM init function, and technically I could have a separate GPIO init and an external interrupt init, but I actually put both of these into one file. Okay, if you do it differently, that's I guess okay, but I put both the external interrupt init and the GPIO init into one function, GPIO init.c. Right, you also need to create separate files for PWM ISR, ADC ISR, and the external interrupt ISR. Okay. Key reminders here. I don't want to hard code values, all right, as much as possible. The reason for that is you're going to modify this code later, all right? You're going to need to continue to modify this code to get it to function with the boards that your electricals have designed. And so to do that updating, The important thing for you is that you're going to have to remember, you have to be able to find all the different things that you made. Okay, so I recommend that you use variables and constants as much as possible. All right, so you can modify this code. All right, and the other thing is you should create some constants for yourself using the hash define statements. Probably put those hash define statements in project.h so that they have global visibility to your functions. Okay, for instance, 2pi. All right, 2pi is a constant you should create, which should be the value of 2pi. Okay, it's probably going to be useful to have the PWM frequency. Okay, there could be others as you go through this. Okay, but this is an important thing to remind ourselves of, that we shouldn't hard code. Now the rest of this of the slides here talk about specific things that we need to do. So let's just look at a couple of quick examples. I don't want to go through all of this because there's a lot of slides here. All right, so main.c. So what I talk about here is what your main.c function should be. Right, so I give specific examples very similar to what you had before. All right, and then I basically talk about what you need to do in your initialization in main.c. So you need to set up the PIE vector table. This tells the microcontroller where all the interrupt service routines are located. Okay, I describe how to do this in the section called interrupt setup. I then need to call the PWM Init and ADC Init functions. What I need to have in those functions is described in the PWM Init and ADC Init sections. Or specifically, I should say the PWM Init and ADC Init sections of these nodes. Okay. I need to set the IER register. Okay, so if I want to know how to do this, that's described in the interrupt setup section of these nodes. I'll need to figure out the PIE IER registers for each PIE block. That's described in the interrupt setup section of these nodes. And then I need to enable global interrupts by calling the eint macro. All right, that's also described in the interrupt setup section of these nodes. Okay. All right, now the rest of your main.c, ERTM, all right, that's allowing a real-time global interrupt. It's a macro. You can look at how it's defined. It needs to be there. Just put that in your code, make sure it's there. And then what I have is a while statement, okay? That while statement basically says while true, all right? So basically anytime the thing is on, if I've reached this code, keep running whatever's in this while loop. It's a NOP, right, or no op, which is an assembly function for no operation, which means do nothing. So we're essentially in a do nothing loop. So our main code does nothing. All right, that's not uncommon in embedded systems. All right, what we have is our interrupt service routines. So the ADC ISR, PWM ISR, and external interrupt ISR are basically doing all the work. Okay. All right, now I describe a couple of other things in here. So eallow and edis, I describe what those are. I have certain registers that are eallow protected. Okay. Now I make a lot of reference throughout these notes to the system control and interrupts guide. All right, and as needed to the PWM reference guide and to the ADC reference guide. Okay. So just to again kind of describe what's here, right? So each of these sections describes what I need, all right, for certain individual sections or for certain, individual pieces of code. All right, so the last pieces here, the last couple of sections describe specifically how I want to set up my PWM init, ADC init, and my various ISRs, okay? So, I mean, just, kind of as an example of what I'm talking about, I'll go ahead a little bit. All right, so if I'm using the interrupts here, I basically I've defined the various 5 steps that need to be included, right? So adding the address of the ISR to the appropriate location of the PIE vector table, setting the appropriate bits in the IER registers, setting the appropriate bits in the PIE IER registers, clearing the int m bit, and performing any peripheral specific setup. All right, so there is peripheral specific setup to enable interrupts. When I say peripheral specific, so I have interrupts coming from peripherals, meaning the ADC, the PWM, and the GPIO. right? The GPIO is where the external interrupt is coming from. Each of these things, GPIO init, ADC init, PWM init, also have some interrupt setup included within them. All right, so you're going to need to look at that stuff, and I kind of point you in the right direction in those sections. All right, just as an example, all right, I'll let you guys go through this later. All right, a lot of stuff kind of described here. All right, so PWM init. All right, so it tells me, for deliverable 1, I'm still using ePWM 1, kind of tells me sort of a couple of things that I need to do, right? So in other words, most of my setup is the same as it was before, right? What I want to have is I want to have a 30 kilohertz PWM, and I say that I initialize everything. I initialize my duty ratio to 0, okay? Now, I've talked in class before about our finite state machine, all right? The finite state machine is what actually changes the duty ratio from 0 once I go into the run state, okay? I need to add a couple of different things, to my code. So I'm going to need to configure the PWM interrupt, all right? So this section of the notes talks about how to configure the PWM interrupt. And for part 2, or I guess what I've been calling step 2 of deliverable 1, right, I will need to use the PWM signal as the trigger for the ADC. In other words, if you remember, the ADCs have a start of conversion signal that tells the conversion to start. In other words, to start the sampling process. The ePWM1 signal is going to be the trigger for that. All right, so I have basically 2 elements of additional setup that I need to include. Okay, and how to do that is kind of described in this section of the notes. ADC init, I describe similarly. Okay, and I also talk a little bit in here, basic things that I need to do in the ISRs. All right, so I talk about some things that I have to do with my ISRs, right? So there's some things that I have to do about global scoping of my variables or certain key variables. And I talk about this PIE ACK bit, all right, something that I need to deal with to be able to get out of ISRs, okay? And how to define ISRs, okay, which need to have this additional interrupt qualifier in the function definition. Then I talk about the specific needs of each interrupt. So the xint ISR, all right, the xint ISR contains the finite state machine that we talked about, okay? So here I talk about what's included in that finite state machine. And I talk about what you need to add to be able to go into deliverable 1 step 2. And I've got similar descriptions of what go in the PWM ISR and the ADC ISR. All right, so there's a lot here which is meant to really kind of guide you through the process of how to utilize the data sheets to be able to select the bits that you need to configure things, and sort of walks you through the code that you need to write. So the code you need to write really falls into the ISRs. That's where all the code lives for our firmwares, inside these interrupt service routines. Okay. So from this material, you should be able to get going on writing your firmware or completing the firmware that you may have already started. All right, that should help. Now, there'll be a couple of additional videos that'll talk about how to calibrate the ADCs. That's the only other real item that we need to worry about.